speedy way. And then we'll jump to chapter 2, which specifically talks about hardware. All right, so principle of operation of the industrial controls we're talking about, right? Here is a mixing process. One of the most simple automated processes you might have, and it consists of something that automatically stirs the liquid in a vat when the temperature pressure reach a preset value. So there's a lot of these applications anywhere you have a need for a mixture, right? There's got to be some way of doing that either manually, semi-automatically, or completely automatically, right? So in our case, we'd like to automate this process, but also it's got a manual operation. So we got, how many inputs can you identify on that process by looking at the schematic, and how many outputs you think we'll need, at least visually there? What do you think? How many inputs can you see there? Three. There's 3 inputs, definitely. And 1 single output, right? You could enhance this by adding a few more things if you wanted to. There's usually some form of a security system on these automated systems. As a matter of fact, security is a big deal in industrial control systems. So because this is a simple idea, that's the way it's presented. But you could have, for instance, a cover on that tank where no one and nothing can fall into the tank and be trapped, right? And for that, you'll have a cover, which will have another input, which will be a micro switch, that if the cover is open, that thing will not turn on, right? So that could be another enhancement. You could also have pilot lights, which will be outputs again, right? A pilot light that indicates when the system is running or when the system is off, right? A pilot light when the system halts. So you could keep on adding more things to that to make it a little more elegant. But to make it a point, this is how the motor operates, right? Again, remember, PLC controls are control devices. And so in this case, the function of the PLC is to run the motor starter coil. And the motor starter coils actually make things happen in terms of the power needed to run this application. So we got the temperature switch and the pressure switch in line or in series, and in parallel with the manual push button. That means you can override your operation if you wanted to by doing that manually. Okay, so that's an application. And there, the same input field devices and push buttons are used. And here is the indication of how you will connect those on the actual input module. And they'll be hardwired to that input module part of the PLC. Okay. The PLC method for controlling the motor will be similar. You're going to have a starter coil, which is going to be hardwired on the output module. All right. And again, we want to send a low power electrical signal, 120 VAC at the most, that will control that thing that controls the big load, right? So in this case, it's a motor core starter that actually is the main element to actuate or activate, whether that's a 2-phase, 3-phase motor or something like that. Here is a ladder logic program, which is one of the main programs you're going to learn to program in PLCs. You have symbols that represent instructions and the numbers that represent instructions addresses. That's kind of critical. Some of the things that we're going to be seeing here in lecture are kind of fading out a little bit, but I'll make the points where that's necessary. For instance, the newest software we're going to be using has a little bit of a different addressing method, and that is using what they call tags. So yeah, I put a label on the instructions, and they'll be equivalent to the input addresses. But addressing is important because it's how the computer will know where to go to retrieve a piece of data, information, right? And what to do with that. And so that's a ladder logic program represented by basically 4 instructions, which represent the 4 IOs, the 3 inputs and the 1 output. All right, for the program to operate, the controller is placed in the run mode. So the controllers have basically 3 modes: remote, program, and run. And those modes can be changed by software and sometimes by hardware. So to run, you have to put it in run. And then you're going to have the controller examining what's happening in the input devices. It's going to bring that data and compare it to the program that you have instructed the control to do. And then we're going to change the output accordingly based on that idea of the scanning, right? There's a scanning cycle that is taking place. The controller is reading what's going on in the outside world, how that information compares to the actual instructions, and what needs to happen to control the devices you're trying to control. So the coil, in this case, output 1, will be energized when contacts I1 and I2, or input 1 and input 2, are closed, or when contact I3 is closed, which is the man in the push button. Either of those instructions will provide a continuous logic across the run that includes the coil. So that's a basic operation of industrially automated control systems. So there is a simulator. By the way, I mean, there's all kinds of applications that you actually can use. This has happened to be a Logic Pro simulation software, which I think you can get a free copy. But again, because the real software is now available, it might not be, I mean, it's optional. I mean, you can actually use that software to design and prototype programs, but I'd rather do it on the real software. The reason being is this Logic Pro simulation does not translate the simulation programs into actual programs. So there's a gap in there. And again, with the new software, you can do exactly this: test, prototype, run, and simulate, and eventually deploy onto an actual platform. So the new software is nicer in that regard. All right. Typical wire required to implement the process using a fixed PLC. Remember, we talked about different kinds of PLCs, one of them being the compact or single PLCs. That is, they have no moving parts. And just like any compact piece of electronics, they're disposable, right? Something goes wrong with these guys, you got to replace them, right? So that's a single PLC. They even got a little screen where you can manually or with a programmer be able to program what you want to do. So this will be the actual electrical configuration, right? We have line 1 that will be distributed across the Q1 point and feeding all the input elements into the corresponding inputs. Of course, the PLC itself needs to be powered. So notice that L1 goes to L1 and L2 goes to L2. Nothing happens if these 2 wires are not there, right? That's the main power line to the controller itself. And then you have a way to connect and control the output, which in this case is the coil of the motor. And to make a good distribution of your electrical circuit and not overload one single line, it's a good idea to kind of balance that load. You can see that the inputs are on L1, whereas the output are on L2 as a way to balance that. All right, so you can modify your programs. In this case, we still have the same elements, but we are rewiring so that now there still need 2 conditions to be able to run that application, right? So either the pressure switch and the temperature switch have to be on for the motor to run or the application to run, or the manual and the temperature switch, right? So You still have two conditions to run that. All right, you modify your ladder logic likewise by moving things around. Um, but here's the key. If you're using a PLC like we're discussing, you basically will need to modify the electrical connections because the sensors are on the same terminal, right? You will have to modify your ladder program. And that's one of the advantages we talked about, right, before. So there's a simulated version of that. So if you happen to have time, you want to play around, Logic Pro has a demo version of this software. Again, I think one of the advantages is the low computing capability of the software, but on the downside, the disadvantage is you cannot translate these programs into actual real programs. It's only for simulation purposes. All right, PLCs versus computers. They're meant to be run on industrial environments. That's the basic idea. Um, there is some form of programming language that you have to deal with in the PLC. All right, they execute, like all computers, a single program in an orderly way, sequential function, such as monitoring the inputs, executing the program, changing the outputs. All right, you can also troubleshoot because we now have a lot of lights, indicators that you can read the faults, and many of the operation manuals will tell you, of some faults, but some faults are evident. Such as when the controller is faulted, when the battery has gone wrong, and actually have gone to places to where machine has stopped essentially because power went out and the battery of the PLC went out too. And so you just replace that. They don't run out pretty quickly, but something like that could happen. PLC programming software. This is a little bit, again, outdated. There's a software called RS Logix, which is a software of Allen Bradley again, still used on legacy technology, but it's staying a little bit behind. If you have a machine that uses RS Logix and it doesn't take any other programming language, that's okay. But most equipment today, you can program in multiple languages. And some companies that produce hardware and software have either added on more than one programming language possibility or the full standard IEC that I mentioned to you, which consists of 5 different languages. We'll talk about that as we go forward here. So that's RS Logix. All right, here is a PLC HMI that you actually can monitor and control. We'll see if we can get to the point of building a few little basic HMI screens so you guys have an idea about that. And there's all sorts of software options to build HMI applications, right? And so that's that. A trendy word that I've heard in past, I don't know, 5 or 10 years is the idea of PACs, as it stands for Programmable Automation Controllers. And the idea here is how can we make the PLC more like a computer while we maintain the ruggedness, right, of a PLC? And so that's happening. I think in this days and age of open source ideas, there's all sort of startup companies. And I mentioned too, there's PLC brands as there are cars, right? And so you have a lot of different options happening, although the big ones are still in the market. All right, so you have PLCs that you actually recognize them based on the number of IOs that you have. A nano PLC will have probably less than 15, usually much even less than 15.8, IOs, points, excuse me. And then you have the micro type, which is the ability to have 15 to 128 IO points. The medium, which will be 128 to 512 IO points, and the large type over 512 IO points. Typically, There's not a ratio of inputs versus outputs, but of course, we always need more input than output, right? So you already saw in that application, for a single output, we needed 3 outputs. So more or less 3 to 5 is the ratio. So I'm guessing in this instance where you have a 15-point IO, you're probably going to have 10 inputs and at the most 5 outputs, right? So that's how things are. This is for the various kinds of PLC: nano, micro, medium, and large. All right, single lightning applications. It's one PLC controlling one process. And again, this is typical of individual machines. You can have a machine that will have a PLC rather than a production line where you're going to have network PLCs that are going to be talking to one another. So that's an example of a cutting operation. And you can see the PLC operator interface, motors, output modules, the stock, the sensor, and so on and so forth. All right, there is a multitask PLC. In both one PLC controls several processes. Now, this is probably a large modular PLC. This is a production line conveyor system where you have engine blocks coming in, operators that will do some, hand assembly in companion with automated machine assembly, and then some adjustments that will be either manual or automatic, and then the engine going out. So that's a production cell almost where a PLC is controlling. You also can have a control management PLC applications, which involves one PLC controlling several other applications than PLCs. So basically, you have a little network, right, of PLCs interacting with other PLCs and other peripherals on the network. Nothing that we're going to be working in here. There's actually full degrees on what we're talking about. You guys know that. I once upon a time taught at a school in Indiana that had a Bachelor of Science in, let me see if I recall that, automation and control systems, right? So the graduates will specialize in using all sort of automated systems. And, they'll have to build networks and, work cells and stuff like that. Memory on PLCs, I think I mentioned that. You're not going to have a lot of memory, although that's actually growing more and more. But PLCs use memory very wisely because of the type of programming instructions that are used. Almost not exactly machine language, but close to that. So there you have our MicroLogic 1000. You can have 1 kilobyte up to 20 inputs, 14 outputs. You don't need a lot for that. Slick 500, you have 64K up to 496 inputs and outputs, and then you have a control logic with 2 to 32 megabytes of memory up to 1 time. So you can see that PLCs use memory very efficiently, right? And they don't use a